optical activity is really cool because it's a physical property of organic molecules. It's not really one we've seen before, and basically two enantiomers have identical physical properties, such as like melting point, boiling point, solubility, but they don't interact with other organic or other chiral molecules the same, but then they also don't interact with light in the same way as well. And specifically, plain polarized light. Okay. All right. So basically, we have a light source, and that light consists of electromagnetic waves that kind of oscillate in all the planes, perpendicular to the direction that it's traveling. And so we have a polarizer, and that's actually going to kind of filter out all of the light except for light that is traveling in the direction that we want, which would be up and down in this case, right? And so plain polarized light has an electric vector that oscillates in a single plane, which is the up and down direction in this case. And basically that polarized light goes through a sample, the organic material that I've drawn in there. And if it's a chiral substance, it interacts with it in a really interesting way, and it actually rotates that plain polarized light. You can see kind of how this vector is going up and down, and then it's kind of curving, and it rotates 90 degrees in this case. At which point it goes through an analyzer, and that analyzer is basically there just to see what angle that light has been rotated. So you're free to move that analyzer back and forth, and then once you can actually see the light coming through, then that's the angle that you would record for your value. That angle is the observed rotation, represented by alpha. Okay. All right, so observed rotation, because you are observing it. All right, so it's basically, this is like I said, a physical property, and the angle that the light is kind of rotated is unique to a specific organic molecule, but it doesn't work for every molecule. So compounds that rotate polarized light are said to be optically active, and these are going to be enantiomers or chiral substances. Now, as you might have guessed, achiral substances they don't rotate plain polarized light, and so they are said to be optically inactive. All right, so now I guess just a couple more like vocabulary words or terms. In this particular example above, we rotated the light to the right, but if we rotate it to the left, then that would kind of be different. It's more indicative of I guess each enantiomer can rotate it to the left or the right. Okay, and so that rotation clockwise or to the right is called dextrorotatory, aka represented by a D or a plus sign. Okay, so rotating to the left or counterclockwise is called levorotatory, aka L or a minus sign. And so the rotation of this plain polarized light has no relationship to R or S configuration. So, for example, let me draw a molecule out for you. This particular molecule right here has an S configuration. Okay, but the way we would write it out, and if we were going to write the name, is S, the dash with the negative symbol to represent that it's levorotatory, and then a dash glyceraldehyde. This other compound is also S, but we have a positive or dextrorotatory rotation for that lactic acid. Okay, so this is just to point out that they're both S, and they both have different directions for that plain polarized light. Okay, so this compound right here is R, lactic acid, and I drew this one specifically just to show you that R lactic acid would be the opposite of the S lactic acid. And that is to say that enantiomers rotate plane polarized light in an equal and opposite direction. Okay, it's the same magnitude, but it is in the opposite direction. Okay, so if it was plus 25, it would be negative 25 for the other. Okay, and then this is, of course, when we are given the same concentration for that particular sample. All right, so we want to be able to standardize this technique, and so we have something called specific rotation. Specific rotation is represented by alpha in brackets with the subscript D. And this is just optical rotation under standard conditions. That way you can do this in Germany and communicate your findings to me in the US, and we can kind of duplicate those results no matter where we are in the world. So specific rotation is equal to the observed rotation in degrees over the path length, which is usually 1 decimeter or 10 centimeters, times the concentration, and that's going to be in grams per centimeter cubed or grams per mil, and that is equal to essentially alpha over L times C. These are standard conditions. And we might have like a concentration of 1 gram per centimeter cubed, for example, and then a path length, again, of 10 centimeters or 1 decimeter. And then the light is 589.6 nanometers. And that's actually why we have that subscript D, because that D represents the D line emitted by a sodium lamp. Okay, so not super important, but just definitely something for your information. Like, what the heck is that D for? Well, that's what it is. Okay, you don't need to wonder anymore, right? So temperature, 25 degrees Celsius. Of course, we got to have that standard temp as well. So let's hit a practice problem or an example. We isolate a product. We have the observed rotation is positive 10 degrees. Our path length is 1 decimeter, and we have a concentration of 1 gram per 10 milliliters, right? Okay, so what is our specific rotation? Well, plug and chug, right? Do you plus 10 over the path length times the concentration, and let's see, that multiply by the reciprocal, that gives it 100 degrees for that specific rotation for that molecule. And that's how it's done. You just plug in the numbers and then you're good to go. You just got to make sure that you have your decimeters. If you're given centimeters, for example, you want to convert that or at least keep that in mind. Okay. Now, I have a hypothetical situation for you that's going to lead into the next kind of topic. So what if I let that sample just sit there on my bench top, and I checked just to make sure and just checked the observed rotation, and it went to 0. I'm like, what? Did I get it wrong the first time? What's going on? Is this a different sample? What we want to remember is that enantiomers rotate polarized light in an equal and opposite direction, right? And so that's basically the answer to this question. And if for example we had a positive 10 degrees, the other enantiomer would be a negative 10 degrees, right? So what if we had a 50-50 mixture of R and S configuration, or a 50-50 mixture of R and enantiomers? What would that result in, and how would that affect the angle of the observed rotation? Well, plus 10 would cancel out with negative 10, and that gives us 0 degrees for our optical rotation. Oh, dang. That's for a 50-50 mixture, which is also called a racemic mixture. Okay, it's also called a racemate. Okay, and that is when we have an equal amount of 2 enantiomers. And since those angles actually cancel one another out, it gets a little bit misleading, as you can see. Kind of what I was trying to tell you in the example is like it went from 10 to 0, but maybe something happened and the compound isomerized and changed basically from a racemic mixture or a racemate to the perceivably optically inactive compound, which would because those two angles were canceled out. And so it is misleading, but it's actually something that you just want to be aware about, and you'll be aware of this possibility if you are familiar with the structure of your compound, which if you're doing optical rotation you would be by now. So let's talk about enantiomeric excess. So this is also called optical purity, as you can kind of see why, because enantiomers give you the nice clean specific rotation. So enantiomeric excess is also abbreviated EE, and the way it's calculated is the percent of one enantiomer minus the percent of the other enantiomer. So, for example, if we have 95% of compound A, we have 5% of compound B, what is the enantiomeric excess of A? We have 95 minus 5, gives you 90% EE of A. So that's pretty easy, right? We all know subtraction. 85% of A, 15% of B. That gives us an enantiomeric excess of 70% of A. Okay, so where it's not really tricky, it's just a little bit different. You have to think maybe a little bit more, is when we have an enantiomeric excess value and we have to figure out the percentages of compounds A and B. So let's say we had an enantiomeric excess of compound A and it was 90%, right? So 90% excess, and that means that 10% of the rest of it consists of 50%, or I'm sorry, 5% A and 5% B. That means we have 90% plus 5%, and that gives us 95% A and 5% B. Okay, so really what you want to do is take an enantiomeric excess and subtract that from 100, and then divide that by 2, and then you got the amount of A and B equally. So in this case, 75%, the difference is 25, cut that in half, gives you 12.5 of A and 12.5 of B. And then you add that to your A, and then that's really all you have left of B. So in this case, 75 plus 12.5 gives us 87.5% A and 12.5% of B. And that's all she wrote. All right, so one last thing before we're done with optical activity. We've got an enantiomeric excess is equal to the observed rotation of the mixture divided by the rotation of the pure enantiomer times 100. So that's the relationship between these things. And so what we can do is kind of go back and forth, right? Anytime you have 3 different variables, you can have a variety of problems with given 2 of those variables, and we just plug in and figure things out. So that's the case here. We've got MSG has a specific rotation. We got that alpha D of positive 24. Solution here is really the mixture, and that has an observed rotation of positive 10. And so the pure enantiomer, of course, is at 24. So we've got 2 of the variables, right? So just do 10 divided by 24 times 100. And let me get my calculator. Bada bing, bada boom. What is that? I feel like I should be able to do this in my head right now, but I can't. Sorry, one second. Should have this ready for you. It's 42%. So that would be the enantiomeric excess, because remember, really what this means is that we have another enantiomer in there, and that's kind of throwing off the angle that the light is being bent, and so, or rotated. Now, if we have our enantiomeric excess, we can go backwards and solve for, in this case, the observed rotation for the solution. So, only if we know the pure rotation. So, what we're looking for is alpha mix. We have positive 24 for the pure enantiomer, and we have 80% excess, enantiomeric excess. So we just do 80 times 24. That gives us a 19.2 degree rotation. Okay, so That's pretty much it. But I got a good joke for you. Of course I do. We're talking about optical rotation. How could you not make a joke about that, right? All right, where's Jess coming from? And on this one, I don't see how that you can make a joke about optical rotation. That's silly, right? Okay, well, it's kind of weird. Like back when it kind of rained, it used to rain, and I was taking a little stroll, enjoying the fresh, crisp weather after a nice rain. Saw a rainbow, and it was a long hike, so like I was really hungry. And they say taste the rainbow, like Skittles. And so but I was really hungry though. And so, you know what? I was just like, whatever, I'm gonna taste this rainbow. So I ate the rainbow, and it was delicious. But I was still hungry because, all it was a pretty light meal. Ooh, get it? Did it go over your head? All right, maybe next time. You can't win them all, folks. You can't win them all.